This is the problem-solving portion of lecture 17 on quotient groups. Now, I've mentioned a bit earlier that we would do some examples of what I call subset multiplication. Now, Barnard, the first author of this text, uses some utterly forgettable, long-winded term that I have no intention of using. I simply call it subset multiplication because that's what's going on, in a sense multiplying two subsets. So we'll do some examples of that. Now let me give the motivation for this kind of thing that I'll explain in a minute. And I've mentioned this before, so it's a bit of revision. Where this whole lecture is about quotient groups, right? And a quotient group is a set of cosets. That's what a quotient group is. So you need a binary operation on those cosets. Those cosets are members of the quotient group, and a group, by definition, needs a set and some binary operation on the members of that set. Now, if your set are cosets, which are just sets, so in a sense, your quotient group is a set of sets, okay? Your cosets are members of this quotient group. So you need some kind of binary operation on those cosets. So this binary operation on cosets, or just sets, right? So imagine this is a coset, this is a coset, and it has elements AI. So we'll just generalize. Forget about cosets for the moment. Just think in terms of subsets, or just sets. So A and B then are subsets of your group G. See? So A is a subset of G and B is a subset of G. Right? And these are the elements of set big A, and these are the elements of set big B. Now, the subset multiplication, this process, written just AB, in a sense you're multiplying, and that's between quotes, right? So 3 bars, so by definition, is defined as all possible ordered pairs where AI are members of big A, one subset A, and little b, which are the members of your second subset B, right? B is a subset of G, A is a subset of G, okay? For all possible ordered pairs, okay? So that if the size of this subgroup A is M, so imagine you have M members here, and the size of subset B is N, so you have N members in this subset, okay? Then the size of this set, you will have M times N possible ordered pairs. So the size of this set will be M times N. Now, what's going on here? Well, you take a member of your first subset and binary operate on it with a member of your second subset. Now remember, these elements here are members of some group G. Okay, so this ordered pair, if you like, is a kind of product. And what's going on here is you take the binary operator, little circle here, you take it from G. So this binary operation here is the binary operator of G, of your group. Okay? So you perform that binary operation on all possible ordered pairs of your two subsets. Okay? And that is what subset multiplication is. It's what I'm calling this. I find this a far better term than this long-winded, forgettable label that Barnard used. So I much prefer, because that's just what it is, right? It's a kind of multiplication of subsets. So it's clear and it's short and it's easily remembered, right? So, okay, so with that theory, you're doing this kind of thing for quotient groups these subsets are now cosets, right? So in other words, if you have two cosets of your group G, your M and your N will be equal, right? Because cosets, they're all the same length, given your subgroup, your H, your normal subgroup of G. All right. The questions at the end of chapter 17, exercise 17, has parts. I'll just give you bits just to illustrate the principles as usual. So question 1 has 4 parts. I'll just give you the last part. It's taking place within the context of group D3, right? So it's your group. So this is question 1, part 4, and your group is D3, right? Dihedral group of equilateral triangles, so the symmetry operations of the equilateral triangle. And I've written out here the group table for D3, and later we will need the group table for Q4, the quaternion group, right? That's a bit later. So I've written out the 2 group tables that we'll use in this problem-solving session. Okay, so D3, so the dihedral group D3, and we're given 2 subsets. So A is a subset of this group. Now remember, it's a dihedral group, so we'll have 2 generators, A and B. And here, the presentation, remember, of the group D3 is the list of generators. Well, they're just A and B. A and B. And you can just see, with those 2, you can generate all the members of the group, right? And it's a group, so it's closed, of course. And the other thing you need in a presentation, besides the list of generators, is relations between the generators. So now for D3, A cubed is the unit, and B squared is the unit, and ABA is B, right? And from these relations, you can calculate, using a bit of algebra, I've done this before, you can calculate the group table, all the elements in the group table, such that if there's a B term, it's on the left. Okay, so in that form. All right, so A now is a subgroup of D3, and its elements are B, BA, and BA squared. Right? And subgroup B, we're given, its elements are B, A, and A squared. All right? Now, just we now, okay, we know the elements of A and B, so we're now just going to do this. So you find every possible ordered pair where all of all the A's, little A's in big A, and all the little B's in big B. All right. So in practice, we've got 3 members of A, 3 members of B. So let's actually do it. So AB, that'll be that times that, and then that times that, and then that times this. So 3 terms there, and 3 more with BA times E, and BA times A, and BA times A squared, and then 3 more, so 9 in total. BA squared E, BA squared A, BA squared A squared. So let's write out those 9 terms. So BE, okay, BE, here, here. Right? We're systematically finding all possible ordered pairs. So BE, and then BA, and then BA squared, BA squared. Right? Now, Now this one, you'll get another 3 terms. So BAE. So BAE. And then BAA. So we'll just BA squared. And then BAA squared. So it's BA cubed. Right? And then BA squared E. Well, I won't bother writing in the E's. Right? So that's just BA squared. And here you get BA cubed. Okay? BA cubed. And here you'll get BA to the 4th. BA to the 4th. Right? Now, let's clean that up a little bit. Now remember, we're talking about D3. So B squared's E and A cubed is E. Right? So we can use this, we can clean this up a bit. So, and we can throw out repeats. Now we're talking about a set, and we define a set to have no repeats, no redundant elements. All the elements are distinct, they're all different, right, in a set. Okay, so this is just B and BA, BA squared, BA, BA squared. Now A cubed here is E, right? So this is just B. Right? BA squared. And B again, A cubed is E, so it's just B again. And now BA to the 4th is just BA. Right? Alright, now let's kick out, eliminate the repeats. So we've got a BA and a BA here, so kill that. You've got a BA squared, so kill that. You've got a B and a B, so kill that. BA squared again, B again, and BA again. Alright, so you're just left with, after removing the repeats, you've just got B, BA, and BA squared. Right? And that is the result of your subset multiplication, right? With these 2 subsets, using the relations of D3, right? To help you simplify. So if actually, I hadn't noticed that before, but it's interesting. This is a coset. That's a subgroup.